Hi everyone, this is part 2 of lecture 15. I thought I would try to solve one of the harder problems in this section because it provides some insight about why these are surprisingly hard problems. So we're going to work on problem 4.7.9. It's not in the assigned problems, but it's similar to 4.7.7 and 4.7.8. And if you can handle this one, those ones will seem somewhat easier. So this problem is a black diamond problem, so you know it's got to be a little bit tricky. The tricky part of this problem is that there are a lot of words in the problem without any math that defines what those words mean. You have to kind of figure out what the math is. So we're going to work this problem out slowly and kind of identify what all of these words mean and how to translate that into math. So let's get started. So looking at the words, we see first that for 70% of the lectures, Professor Y arrives on time. As a math fact, what we have is that there's an event L that the prof is late. And moreover, we know that the probability of L complement is 0.7. That is, that probability the professor is late is 0.3. Moving to the second sentence, we see another math fact. When Professor Y is late, the arrival time delay is a continuous random variable uniformly distributed from 0 to 10 minutes. So hiding in that is these words, the arrival time delay. The arrival time delay is a random variable that we never gave a name. So let's let random variable x is equal to this thing we call the arrival time delay. And in words, we have that given L, that the professor is late, X is continuous uniform 0 to 10. So the words of the problem only defined X given the event that the professor is late. Given the event the professor is not late, L complement, X was kind of implicitly undefined. But in this problem, we can say that given L complement, X equals 0. There is no arrival time delay when the professor is not late. At this point, everyone should know what a continuous uniform random variable is. For instance, if we drew it as a PDF, we would draw the following. Since it's from 0 to 10, here's 0, here's 10, and we would draw a box for the PDF. And it would be height 1/10 from 0 to 10, so the area under the curve is equal to 1. The question though is, what name do we give this PDF? And this is another place where this problem is tricky because we never really name this random variable. It's it's not exactly random variable X because X only has a PDF that looks like this when we have the event L that the professor is late. Eventually, when we get to chapter 7 in the book, we'll learn that there's terminology for this. This is called a conditional PDF of X given event L. But in fact, this is a topic we defer discussion to chapter 7, and here we are trying to solve this problem in chapter 4. Here in chapter 4, what we remember is that this PDF also has a corresponding CDF. We could sketch it here. Right, the CDF starts at 0, and then it ramps up, and then it flattens out at 1. And this occurs at 10, And this CDF, actually, we can give a name just from first principles. It's the probability random variable x is less than or equal to x given the event L. And that's a function of x. So, this mathematically, this object is 0 for x less than 0. It's equal to x over 10 for 0 less than equal to x less than equal to 10, and 1 for x greater than 10. Once again, when we get to chapter 7, this will have a special name. This will be the conditional CDF of x given L. But here we are in chapter 4, and we haven't learned that yet. Now consider the other case when the professor isn't late. In this case, we have event L complement, and when L complement occurs, x is equal to 0. Professor's not late. So in terms of random variables, we can think of this as a CDF, x less than or equal to x given L complement. And this is equal to 0 when x is less than 0, and it's equal to 1 when x is greater than or equal to 0. It's in fact exactly equal to the unit step function. Specifically, we have it's 0, and then it jumps up to 1 at 0. Because given L complement, we have that random variable x is equal to 0, which implies that the probability x is less than or equal to, say, minus 0.001, given L complement has to be 0, but the probability x is less than or equal to 0, given L complement, is equal to 1, precisely because x is equal to 0. So now we can combine these pieces to find a complete CDF of x using the law of total probability. This is the probability x is less than or equal to x. The probability x is less than or equal to x given L complement times the probability of L complement plus the probability x is less than or equal to x given L times the probability of L. And we know these two probabilities, probability of L complement, that the professor is not late, is 0.7, and the probability of L is 0.3. So in fact, this CDF is a combination of the unit step function, given L complement, plus the ramp function, given L. One approach that some students like is to combine these two pieces graphically. So the first piece looks like this. It's a step function, but it's multiplied by 0.7. So it jumps up to 0.7 instead of 1. And the second piece is a ramp function. It starts out at 0, and at 10, it reaches 1. But in fact, now it's multiplied by this 0.3, so it just reaches 0.3. At this point, it's helpful to combine these two functions graphically. To do so, we start with an axis. And this combination is actually going to be the CDF of random variable x. So this function is 0 for x less than 0. And at 0, it jumps to 0.7. And this 0.7 is then contributed forever after. But we also, starting at 0, have the contribution of the ramp function. And the ramp function from 0 to 10 adds another 0.3. So what happens is we have an additional ramp that gets us up to 1. Our scaling's not very good, but it's pretty clear what's happening. So this is the CDF of x, and we could find an algebraic expression for it as well. And we could find an algebraic expression for it as follows. It's equal to 0 for x less than 0. It's equal to 0.7 for x equals 0. It's equal to 0.7 plus 0.3 times x over 10 for x greater than or equal to 0 and less than or equal to 10. And it's equal to 1 for x greater than 10. The thing is, this was a pretty hard problem to find the CDF of random variable x with a lot of steps and things to combine, but it's not actually the problem we were asked to solve. It's just kind of a stepping stone on the way to the real solution. Okay, so now let's review and go back to the original problem. And we see that, in fact, the random variable we're interested in is t, the length of time that the students observe a lecture. The random variable we worked on the previous slide was this arrival time delay that we called x. And x had a CDF, f subscript capital X of x, 0 for x less than 0, and 0.7 plus 0.03x for 0 less than or equal to x less than or equal to 10, and 1 for x greater than 10. Since we've worked so hard to solve the wrong problem on the previous slide, let's see if we can use that solution now to solve the problem we're really interested in, the PDF of t. So the idea here is that we can write t as a function of x in the following way. For instance, t is going to be equal to 80 if x equals 0. On the other hand, t is going to be equal to 80 minus x if x is between 0 and 5. Finally, the last key fact is that if the professor is 5 minutes late or more, then all the students get up and leave. In this case, the students don't observe any lecture, and in fact, the number of minutes of lecture observed is 0. And this occurs if x is greater than 5. From this collection of facts, we see that t is a function of x. And we can depict it graphically as follows. We know that x is going to be between 0 and 10. And we know that t is going to be between 80 and 0. In fact, when x is 0, t is exactly 80. And then as x increases, the professor arrives 1 or 2 or 3 minutes late, but less than 5 minutes late, then the amount of lecturing time goes down linearly, so that by the time you get close to x equals 5, the lecturing time is approaching 75 minutes. But exactly at x equals 5, then the lecturing time falls off a cliff because all the students leave, and it goes exactly to 0. And then for x bigger than 5, between 5 and 10, The lecturing time observed by the students is 0 because they all left. So now we can use this function of t as a function of x in order to deduce some probability facts about t. For instance, the probability that t is equal to 0 is the probability that x is greater than 5, which is 1 minus the CDF of x at 5. And so this is equal to 1 minus 0.7 plus 0.15, which is equal to 0.15. Since t can't be less than 0, we have that for all t strictly less than 0, the probability t is less than or equal to t equals 0. On the other hand, at t equals 0, probability t less than or equal to 0 will be the probability t equals 0 will be 0.15. Those facts are pretty simple, but now things get a little bit trickier. For instance, for t bigger than 0, but t less than or equal to 75, the probability t is less than or equal to t is still the same as the probability t equals 0, equals 0.15, because either t is 0 or t is between 75 and 85. Continuing this, if we have t between 75 and 80, we can think about the probability t is less than or equal to t, and we can relate this graphically to our figure. What we're doing here is we're drawing a line, say around this example's line is like t is equal to about 77, right? And we're asking the question, what's the probability we observe a t in this, we observe a t which is either along this segment or along this segment. One way to think of this problem is that we do an experiment and we're going to observe both an x and a t, and then we're going to observe the pair x and t either along here or along here. And what we're doing is when we try to find the CDF of t, specifically probability t less than t, is you find all of the t and x pairs for which this condition happens to be true. In particular, in this example problem, this line segment here is t equals 80 minus x, because in fact the slope is 1. As x reaches 5, t goes down to 75. And so for t between 75 and 80, right, we have is the probability t is less than or equal to t is equal to the probability 80 minus x is less than or equal to t, which is equal to the probability that x is greater than or equal to 80 minus t by rearranging the inequality. This looks complicated, but we're almost done, because this is equal to 1 minus the CDF of x at 80 minus t. And we know what the CDF of x is because we found it way up here at the beginning of this problem. Because t is between 75 and 80, 80 minus t is between 0 and 5. And that lets us use the CDF here in this range between 0 and 10. So we can write that this equals 1 minus 0.7 plus 0.03, where we're 80 minus t because 80 minus t is replacing x in this expression. So it's not exactly clear what the simplest way to write this is, but we'll go ahead with it's equal to 0.3 minus 0.03 80 minus t. So we're now in a position to combine these facts to derive to graphically represent a CDF for t. So we draw some axes. We have small t, the dummy variable, CDF of t. We start at 0. We know that the CDF is 0 up until 0. Then we know that it jumps to 0.15 at 0. Then we know that the function is going to be flat all the way out to 75. Then we know that this expression here starts to take hold. And we look at that expression first at t equals 75. 80 minus 75 is 5. And we have 0.3 minus 0.15. We are still right here at 0.15. And then we see that this function is going to grow linearly from 75 to 80. And at 80, this expression is going to, the expression 80 minus t is going to be 0, and that the curve will then be 0.3, the function. So we'll plot that, the increase in linear to 0.3. We draw a dot over here to line up with that point. And here's our ramp going up. And now at 80, there's another jump discontinuity because we know that the probability t is less than or equal to 80 happens to be 1. So we have a big jump, right? And then the function is flat. And the value here now is equal to 1. So this is the CDF of t. But if you go back to the original problem, the problem actually asked here for the PDF of t. So we have to take a derivative of this function. And the easiest way to do that is to do it graphically. So now we have take a derivative. And so the first thing we realize is that the function is so this is the derivative of the CDF. We realize, okay, so where the CDF is flat, the derivative is 0, so it's 0. But now at this point, we have a jump discontinuity. The height of that jump is 0.15. And when you take a derivative, you get a delta function with a weight of 0.15. So we label an impulse here, 0.15. Then we go and look at the next interval and we're like, oh, here the CDF is flat, so the derivative has to be 0 all the way to 75. At 75, we see that the CDF is a ramp, so the derivative is constant slope, right? The slope here is equal to the rise, 0.15, divided by the length of the run, which is 80 minus 75, which equals 5, 0.03. So now we have 0.03. Here is this jump. That's supposed to be flat. It's not very well drawn. And now here at 80, right, we have another just jump discontinuity. The jump has height equal to 0.7. And the result is we have another impulse, and the weight of that impulse is 0.7. And now, beyond that, the slope once again is 0, and that's what we have. So putting these things together, we have a PDF of t that we can represent algebraically as equal to 0.15 delta of 0 at t equals 0, right? It's equal to 0.03 for t between 75 and 80, right? And it's equal to 0.7 delta of 0 at t equals 80. And we always have to include 0 otherwise, like this includes, for instance, t's below 75 and t's strictly above 80. So this indeed happens to be the answer we were looking for. It's the PDF of t. And it's worth pointing out that this was kind of difficult to find. It required a lot of careful thinking and some algebra and some thinking about what the possible events were. And the final result is a mixed random variable. So we see that in fact there's a probability 0.7 that t will be exactly equal to 80, that the professor arrives on time and you get a full 80 minutes worth of lecture. There's also a probability 0.15 that the professor arrives more than 5 minutes late, and in that case you observe 0 lecture. That's why the impulse is at 0. And then there's a continuous region where the professor could arrive between 0 and 5 minutes late, and it translates to a lecture that's between 75 and 80 minutes long. This is not uncommon, but all of these particular values of t have 0 probability. It's just that we have a non-zero density in this interval. So this is an odd-numbered problem, and for odd-numbered problems, there's a student solution manual. And in the student solution manual, you'll find this simple one-page solution. And this solution is if you look carefully, has exactly the same answer we had on the previous slide, but it in fact does the reasoning strictly using density functions and impulses. So it's worth going over and seeing that, oh, all of these very complicated steps involving CDFs, if you can kind of think carefully, can be avoided. So the first observation is that the probability t equals 80 is 0.7. It's the probability that the professor arrives on time, right? The next case to consider is that, oh, the professor is more than 5 minutes late. And in that case, right, t is going to be equal to 0, right? And the probability of that is going to be 0.3, which is PL, the probability that the professor is late, times 0.5, which is the probability that the arrival time x is greater than 5, given that the professor is late. If you think about it, it's the integral from 5 to 10 of the continuous uniform from 5 to 10 random variable. So all that's left at this point is to account for values of t corresponding to t not equal to 0 and t not equal to 80. And now the problem kind of, this solution kind of makes another semi sort of intuitive insight or guess, right? And it's that because the delay of the professor's arrival is uniform, um, what what they observe is that, oh, it must be that it's uniform, that when t is between 75 and 80, all of those values have the same probability. So implicitly, what the solution is guessing is that we have the following situation. We have an impulse at point one, at 0 of weight 0.15. We have an impulse at 80 of weight 0.7. And then we've got a continuous uniform part between 75 and 80. And the height of this thing has to be some value c. And the final step here is to say, well, in fact, that the area under this PDF of t, if I call this ft of t, has to integrate to 1. So we have integral 0 to 80 ft of t dt. And so I get a 0.15 contribution from the impulse at 0, plus I get 75 to 80 times dt, plus I get a term 0.7 for the impulse that occurs at 80. And this has to equal 1. And so I get that c times 80 minus 75 has to equal 0.15. When I get c is the 0.03 that we already knew was the answer. So in essence, we have a one-page solution here, which if you sort of get the intuition, then you can kind of see easily what the answer is. You see where the impulses are. You see where the rest of the probability is uniform in an interval, and you do a quick calculation, and there you are. But that kind of intuition is kind of only acquired after you've struggled and done it the hard way. The hard way being all the steps we did on the previous slides to find out this arrival time random variable x, and then to find random variable t is a function of x, and then to write a CDF of t, and then to take a derivative. If you don't have the intuition, you have to start with the basics, finding CDFs, and go from there. Thank you very much. This is a problem where in normal semesters I would never do this in class because it's kind of complicated, and at various points on making this video, I had to start over and rewind. And if I were doing this in class with you, I would have gotten hopelessly confused. It may still be confusing as it is, but here in the video world, you have the option to rewind a few dozen times, and hopefully it'll become clear. So this completes lecture 15. And I think I already owe you a start on lecture 16, so I better get going. So long.